Build dense meaning from one-hot words. By the end, you will see one-hot vectors, simple similarity, and how context turns sparse counts into dense word signals. You will build a tiny pipeline that goes from single-word encodings to ranked nearest words based on shared context. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Word embeddings help computers see word meaning. They solve search and clustering problems where exact word match fails. People reach for embeddings when synonyms and context matter. A downside is that naive one-hot vectors treat every word as unrelated. Compared to dense embeddings, one-hot is simple and explainable, but it cannot capture similarity without extra steps. The intuitive idea is to start with one-hot identity, then watch how context connects words. If two words share many neighbors, they will end up with similar vectors. For example, cat and dog often appear near the word pet. That shared neighborhood tells us they are related. We will use a tiny corpus of 5 words and a few short sentences so the steps stay clear and repeatable. We will build a pipeline that creates one-hot vectors, measures similarity, gathers bigram contexts, expands the context window, and ranks nearest words by context overlap. This snippet builds a one-hot vector for a word from a tiny vocabulary. It shows how a single target word becomes a long sparse vector with a single 1 at the vocabulary index and zeros elsewhere. In our toy vocabulary, the vector length equals the number of unique words, so the representation is easy to visualize. The paragraph explains that as vocabulary grows, this vector becomes high-dimensional, and most entries remain 0. It also points out that one-hot is lossless for identity, but gives no notion of similarity. Changing vocabulary order only reindexes positions and does not change relationships between words. Now we will compare similarity between those one-hot vectors. This example measures cosine similarity between two one-hot word vectors to show what that similarity yields on identity encodings. It explains that cosine similarity computes the angle between vectors, which for one-hot vectors is 0 when words differ and 1 when they match. The example uses cat and dog to demonstrate a 0 similarity and shows that identical words return a maximum. It also discusses that with one-hot inputs, cosine is a strict equality test, not a semantic metric, and that introducing weighted co-occurrences or context vectors is necessary if we want meaningful, non-zero similarities between related words. Next, we will extract immediate neighbors using bigrams. This code extracts immediate context words for a target using bigrams and shows how to collect left and right neighbors into a context bag. The explanation walks through sliding a 2-word window over the tiny corpus sentences and recording which words appear next to the target. For example, it lists words that appear immediately before or after cat in our sample sentences. It clarifies that this immediate context captures syntactic neighbors and common collocations. It also describes how changing the target word or adding sentences changes the collected context frequency counts and the downstream similarity between words when we compare their context bags. Next, we will widen the context window to include next nearest neighbors. This snippet widens the context window to include next nearest neighbors and explains the difference that a larger window makes. It shows that increasing window size from 1 to 2 captures words 2 positions away, which adds more co-occurrence counts and smooths rare signals. With our tiny corpus, that change turns a sparse co-occurrence matrix into a denser one and often raises similarity between related words like cat and pet. The paragraph also discusses trade-offs, noting that a bigger window can introduce noise by mixing distant topics, while a smaller window stays focused on local syntax and immediate semantic roles. Finally, we will rank words by their shared contexts to find nearest neighbors. This example ranks nearest words to a target via context overlap similarity and walks through converting context bags into numeric vectors, then comparing them with cosine or dot product to get a ranked list. It describes creating a context vector for each vocabulary term from counts of neighboring words, then computing pairwise similarities and sorting to produce nearest neighbors for a chosen target like cat. The explanation highlights an adjustable parameter top k and shows that increasing k returns more candidates but may include weaker relations. It also mentions that using weighted counts such as frequency clipping or inverse document weighting changes which neighbors rise to the top. Recap: one hot gives unique identity but no semantics. Context vectors create meaning by counting shared neighbors. Use a controlled window to balance focus and noise. Next step: scale this exact approach by tuning the context window and then measure quality on a larger corpus. Or add an approximate nearest neighbor index to speed up ranking for thousands of words. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.